Today what we're going to do is we're going to look at the 3 examples that I've sent through on the group. And we're looking at them because I want to do an example of the work energy theorem and various ways of calculating work done, okay? And also calculating force, etc. I want to look at an example relating to conservative or conservation of mechanical energy and conservative versus non-conservative forces. And I also need to do an example that talks about just the conservation of mechanical energy. So there are 3 very big examples that we need to do. Okay. Now the first one I'm looking at is the one that starts with the wording that says a trolley of mass 2 kilograms is initially at rest at the bottom of a runway. It is pulled up the runway, which is inclined uniformly at 25 degrees of the horizontal by a constant force of 100 newtons. It travels a distance of 8 meters up the incline. The trolley experiences a constant frictional force of 50 newtons. The first question says determine the net work on the trolley, and the second question says determine the velocity of the trolley. Okay, so one of the first things that I do in questions like this is I draw a picture. Not a diagram that is scientifically correct, okay? So I'm not talking about a force diagram or a free body diagram. I draw a little bit of art as such to give me an idea of what I'm dealing with this kind of question. So my artwork for this one will indicate the fact that I have my 2 kilogram trolley over there and it's going up the slope. It is so important. So important in these questions to write down what your direction of motion is. So when I do this, I'm also going to say that that is my direction of motion, because sometimes what happens is we have a force applied, but the force applied will allow the block to slide down the ramp, okay? Whereas this wording says that the block moves up the ramp. Do you understand what I mean? Because sometimes you can be holding something and you can allow it to slip downwards. Okay? And the direction of motion is important because we have to decide which direction friction will act in and which direction the rest of the forces are acting in. And if you get that wrong, then you lose a lot of marks just because you didn't draw an arrow on your diagram. Okay? So the first thing, some artwork, and an arrow that tells us what the direction of motion is. Then, I have my angle of 25 degrees. Are we okay with that? All right. My angle of 25 degrees, and I know that it's 8 meters that moves up the slope. So from that point to that point is my 8 meters. So it's a given list in pictures. Good. Now, the first question of these, the first part of these questions usually asks us to either draw a force diagram or a free body diagram. So just as a recap, what is the difference between the two? If I draw a force diagram, I'm talking about a picture with a block, yes? And I'm allowed to do my arrows in any directions. So I can put the arrow towards the block, and I must place my force where my force acts according to the diagram. The other thing we can draw is a free body diagram. A free body diagram is just represented with a dot, and what that means is we're allowed to put the arrows only from the center outwards on a free body diagram. The first thing I'm going to do now is draw a free body diagram for this particular example. So my free body diagram, I'm going to start off by drawing the ramp. It is the number one mistake that you make when you're doing these problems. You choose not to draw the ramp, and I don't understand it. So for many of you, you will choose to draw on the horizontal even if there's a ramp involved. If there's a ramp, put your object on a ramp, okay? Because it helps with the angles. So for a free body, I will have a dot. And there are a couple of things that are always present, always present. The first one being FG. So FG, remember, always acts directly downwards, yes? The other thing that we have is Fn, and that's my normal force. My normal force is perpendicular to the ramp. Notice that my normal force is not in the opposite direction to Fg. Because we have a ramp involved, Fg must act directly downwards, but Fm is perpendicular to the ramp itself or to the surface. Do you have a question, Paula, or are you fine? You're fine. Okay. Now, the rest of the forces involved here are obviously an applied force that goes up the ramp. So that's my applied force. And then the other force that's here is the force of friction that acts down the ramp. I can identify which direction friction acts because of the arrow that showed me motion. Okay? It's a really big sticking point for you guys, where sometimes if you don't know which way the object is moving, your friction is in the wrong direction. Unfortunately, it ripples through all of your calculations. Okay? Very, very important first step. Once I have that, let's look at the questions. The question says determine the net work that is done on the trolley. The net work done. Now you'll notice from the pictures I sent through that there are two methods. When I calculate net work done, I can either use the net work by what we call the vector summing of the work done. Now effectively it's not really vector summing because work done is not a vector. But I meant vector summing because we're going to take into account what's positive and what's negative. So we can calculate that using work done as an equation. Are you ready? You ready? Okay. So I'm going to use method 1. The first thing that I'm going to look at is the fact that there's work done by a whole variety of different things here. Every time there's a force, we consider work to be done by that force. So there's work done by the normal force, there's work done by Fg, there's work done by F applied, and there's work done by the frictional force. And we are going to calculate the work done for each of those bits and pieces. Let's start off with the work done by the applied force. It's very important to use subscripts in this section. They actually require you, if you're going to talk about net work, it must be W net. Okay, it can't just be W. I have that, and that's going to be equal to the force applied multiplied by the change in my displacement multiplied by cos theta. Okay, multiplied by cos theta. Are you guys all right with that? Yes? Okay. So, my force applied, the value for my force applied, have they given me the value? Yes, they have. They've told me that the constant force applied is 100 newtons, yes? Okay, they've also told me that my friction is 50 newtons, not so. Okay, so my force applied being 100 newtons, and I'm going to use this multiplied by the 8 that I've moved my object and the cos of my angle. Remember the force applied and the actual slope, they're in the same direction, which means that the angle between the applied force and the direction of motion is 0. I'm going to say that again. The angle between the applied force and the direction of motion is 0, which means it's cos of 0 degrees. And I get an answer. Okay, so I've already worked that out, and that gives me 800 joules of work done by the applied force. The next one is the work done by the normal force. For that, I'm going to have the normal force multiplied by delta x, cos of my angle. For this one, I don't even have to calculate the normal force. Okay? Because I know that the normal force is at 90 degrees to the direction of motion of my actual object. And my rule is, if the force applied and the direction of motion are at 90 degrees to one another, then no work will be done. Okay? Which means normal force, you can multiply that by 8, but remember the angle between the force and the displacement means that this becomes cos of 90, and cos of 90 will give me 0 joules. Are you okay with that? You can plug that into the calculator, but that cos of 90 tells me that it's because the force and the direction of motion are at 90 degrees to one another. And it's because it's perpendicular. Now, the work done by the frictional force, okay? This one we know that the frictional force is going to be equal to that multiplied by that, and the cos of theta again. My frictional force was given to me as 50 in the question, 8 for that. And at this point, I'm going to pause and I'm going to say to you, this is that place where the direction of motion is important. Because my frictional force is 180 degrees away from the movement of my object always. Always. Yes? My frictional force is always 180 degrees from my applied force. Because friction always opposes the direction of motion. Right? Friction is always in the opposite direction. So, I get cos of 180. And that means I get a negative answer for this. Remember, this does not mean that we have negative work done. It simply means that the frictional force removes energy from the system. Okay? It removes energy from the system. And by removing energy from the system, it decreases the amount of net work that is done. It means that this whole system is not 100% efficient. All of the applied force doesn't go into moving the block. Some of the applied force goes into overcoming friction. And there's work done in overcoming friction. Yes? Okay. Now, the last one. The last part of this is obviously Fg. And for this, we need to kind of think about it. Okay? So we kind of need to think about what we're doing when it comes to the work done by Fg. What do you know about the weight of the block in terms of pulling the block up the ramp? Yes?
And the more weight, the harder it's to get up the ramp?
Exactly that. That Fg actually has a negative impact on this overall system in this instance. And the reason why Fg has a negative impact is because the object is moving up the slope. If the object were moving down the slope, then Fg would have a positive impact on the overall work done. Do you understand that? Because then Fg would help the object move down the slope instead of hindering the object moving up the slope. Yes? Are you okay with that? Are you sure? Are you sure? Is my wording absolutely clear? Are you with me? Now to calculate this, I need an angle. And it's a really odd thing because I need an angle between the force applied and the direction of the force. Sorry, the force applied in the direction of the displacement of the object and the direction of the force. If this is the direction of the object and this is the force, then the angle that I'm dealing with is this angle here. Do you see that? It's a very strange thing. You'll notice that when we're talking about F applied, the displacement is in this direction, F applied is in this direction, 0 degrees. For the normal force, direction of motion up, normal force acts that way. So the angle between the two is 90. You can see that 90 there. Yes? If we were talking about the frictional force, direction of motion, frictional force 180 degrees. You see that? Now we're talking about Fg, which means my angle that I measure must be from this point all the way to where Fg actually is. Okay, where Fg acts. Yes.
Why you did that way around?
This way here. Because we've measured this way previously. Are you with me? Are you okay with that? Okay. So, here's the thing. There are actually two options to do this, and I'm showing you the first one. This one works in any instance, and you don't have to think about it too much. The second one has got a couple of T's and C's that we have to take into account. So this is the one that the way that I prefer. To measure that angle, I have my 90, I have 180, and I have this angle here. I know that this angle is 25 degrees according to my rules about inclined planes. That angle and that angle are the same. Those are my rules for inclined planes. Okay? That means that this angle here must be equal to 270 minus 25. I'll give you a second to think about 270 minus 25. 270. Oh, so I have to measure this red angle, okay? I am 25 away from 3 quadrants, which is 270 degrees. From here to here is 90, from here to here is 90, from here to here is 90. 90, 90, 90, 270, yes? And 25 degrees away from hitting that 270 mark, which means that what is my actual angle?
45.
245. 245, are we sure?
If you were confused because you said 170.
Did I say 170? I'm sorry, I meant 270. Completely in my head, I was convinced I said 270. Okay, so over here, we can say that the work done by Fg is going to be equal to the value for Fg multiplied by the displacement multiplied by the cos of theta. The value for Fg, I have to work that out because I've got 2 kilograms, so it's 2 times by 9,8, yes? And for that, I can actually plug that in. I'm totally allowed to just plug that into my equation, and you'll sometimes see in memos, in department memos, how when you look at the work energy bio questions, the equations and the substitutions get crazy because they do everything in one step. You know, and it looks really intimidating, but actually, it's really simple. Then the cos, my angle that I've calculated is 245, and I get an answer of how much, my angels? Minus 66,27 joules.
Down.
Does the negative value make sense?
Yes.
It has to make sense because remember, Fg in this instance removes work or removes energy from the system. Okay? Now, if I want to calculate the net work done, I am going to say the following. I'm going to say that the net work is therefore equal to the sum of all the bits and pieces that I have calculated. Oopsie, I'm out of space. Okay? So I have to add all those things together. And I have 800 for the work done by the applied force. I have 0 for the work done by the normal force. And I have minus 400 for friction. And I have minus 66,27 for the work done by Fg. And then my answer is 333,73 joules. 333,73 joules is my value for the net work done. Let's pause it for a moment. So the second method. The second method we can use is we can calculate the net force before we calculate the net work done. It is entirely up to you which method you prefer to use. I like to use calculating the net work from work done, okay? But some of you might find that force is more familiar to you because calculating net forces is something that we've done quite often. So when it comes to calculating this in terms of method 2, we need to firstly look at the vector sum of the forces that are acting parallel to the plane. So we don't take anything into account unless it acts parallel to the plane. Okay? And for that reason, we're going to use Fg parallel, and that's equal to mg sine of theta. In other words, what we're doing here is calculating this part here. There's Fg parallel, and this one is Fg, and this one is Fg perpendicular. Do you remember it from inclined planes? Okay.
Last year,
Yeah.
they missed him.
last year. But I'm sure I've said it a couple of times. So now we've got mg cos of theta. Now remember, these things are very separate to what we've been talking about in terms of work done. Okay, those are trig functions that have been around for a while. So when I calculate the net work in terms of this, I'm going to be using the force that's applied, I'm going to be using the frictional force, and I'm going to be using Fg parallel. Okay? And for that, I can rewrite that as the force applied. Force applied plus the frictional force, and I'm going to add mg sine of theta. Okay, so I have my 100, because the 100 was what was given to us, 50, but the 50 is negative because it's in the opposite direction and we're dealing with forces right now. And then mg, okay, is going to be equal to 2 times by 9,8 multiplied by the sine of 25 to work out what the value is for Fg parallel. We must also note that that is going to be a negative value. And it's a negative value because this whole thing is a negative value because of the fact that the force that is applied by the component of Fg is negative. It's in the opposite direction, or it's in a different direction to the actual direction of motion. And then once we have that, we can calculate the value for everything, which gives me 41.72 newtons. And this is up the plane, because direction is important when we deal with forces. And my last step here is to calculate the net work. So you can see this method actually looks a lot faster. You see that? The method looks a lot faster, but I find that it's tricky. I find that it's quite tricky. There's my 41.72, I've got my 8 for that, and the cos of 0, and so I end up with 333.76 joules. And that's the second method. Okay.
Ma'am, which one would you say?
I like the first one.
I
I like the first one.
But ma'am, with this one we don't have to like calculate all the angles.
Yeah. I still like the first one. It always gives me a better idea of what I'm doing. I expose you to both so that you can choose that. Okay. As long as you make sure that you know exactly what you're doing with the forces. The first thing they ask you in these questions is to draw a force diagram or a free body diagram. If you get that wrong, then you have no hope of getting the rest of it right because you've written down the forces incorrectly. So please make sure that you pay attention to where the forces are acting. Yes?
Ma'am, you said this example has a few T's and C's. What are they?
Well, for this, you have to understand this part here. That Fg we can use as a total Fg in terms of the other example. Okay? But for this one, we must only use the forces that are acting parallel to the plane. So you'll see in the picture that I sent you, it says vector sum of forces acting parallel to the plane. We only deal with the forces parallel to the plane. We haven't taken into account the normal force. Yes?
Ma'am, did they ask us, so with this example, ma'am said you're only dealing with the forces parallel to the plane, so they wouldn't ask us more questions on forces that are like perpendicular to the
They could
plane.
ask you. They could ask you about those. But then you need to know that the forces that act parallel to the plane don't do any work for us. Okay? The last part of the question in terms of what was asked of you said that they wanted you to determine the velocity of the trolley. Now for this, I'm going to use the work energy theorem. So I'm going to use the work energy theorem to calculate the speed. Because remember, the work energy theorem links speed and work done. Okay? So, work energy theorem simply says that the net work is equal to the change in my kinetic energy. Okay? The net work is equal to the change in my kinetic energy. So, if that's the case, I'm going to write down that my net work is equal to a change in my kinetic energy. That translates to EK final minus EK initial. That makes perfect sense because it's a change in the kinetic energy. for that, I'm then going to say a half mv squared, and it's vf squared, minus a half mvi squared to calculate the change. Everybody still with me?
And would we always use this equation of motion?
This is not an equation of motion. This is the formula for kinetic energy. So calculating kinetic energy says half mv squared. Potential energy is mgh. Okay, so just look back. It's the energy slide. So there's a slide on Google Classroom that relates to the different types of energy. One for kinetic, one for gravitational potential energy.
And they don't give us these formula in our
Data sheet. I'm going to check for you now. You will get the kinetic energy equation for sure. Okay. Now, let's look at how we substitute into that. So I've got the work done, or the net work done, as that, and I have a half the mass of 2. My final velocity is what I'm looking for, minus half 2. My initial velocity is 0 because they've told me that this object starts from rest. Okay? You have it there, Gordon?
Hello, ma'am. Ma'am, did I do well on my left hand?
I'm recording. So we've got EK being half mv squared, alright? And we have net work as a change in the kinetic energy. Okay? Alright. So, but we don't have this. You need to know the work energy theorem. So once we have this, we can then manipulate to get VF out, and we have 18,27 meters per second as my answer for the final velocity of the block. Okay? Make sense? We can stop it right there.
Recording when I say